Okay, so we're going to prove by induction, following by deduction, 2n squared greater than n plus 1 squared, where n is greater than equal to 3. N is an m and n as a natural number. Start off with p of 3. P of 3, we're going to test p of 3, and what we're going to get is 2 times 3 squared. It's greater than 3 plus 1 squared. We're going to have 18 is greater than 16. This is true for p of 1. Now that we have true for p of 1, what we're going to do is we're going to assume true for p of k. So assume true for p of k, where p of k is going to be 2k squared greater than k plus 1 squared. Okay, and k has to be bigger than equal to 3 because it's n is greater than equal to 3. Now we're going to test p of k plus 1. Now, we test p of k plus 1, what we're going to get is 2 times k plus 1 to be squared greater than k plus 2 to be squared. Now, what we're going to do is we're going to multiply this out, and we're going to get 2 times k squared plus 2k plus 1 greater than equal to k squared plus 4k plus 4. That's what happens when you square this out. That's what happens when you square this part out. Then we're going to multiply it out. We're going to get 2k squared plus 4k plus 1. That's going to be greater than k squared plus 4k plus 4. Now, what we're going to use next is an intermediate step. Okay? And the intermediate step is going to involve using p of k. And that's a plus 2, by the way. Okay. So, what we're going to do is we're going to expand p of k, and what we get is 2k squared is greater than k squared plus 2k plus 1. So, if we replace this number here with a smaller number, so what we're going to do is we're going to replace it with we're going to replace this with k squared plus 2k plus 1. We're going to replace that with p of k. So we're going to get here is k squared plus 2k plus 1 plus 4k plus 2 greater than k squared plus 4k plus 4. So we're going to have k squared plus 6k plus 3 and that's going to be greater than k squared plus 4k plus 4. Now if you take away both sides, k squared cancel. Bring the 4k over the other side, we're going to get 2k, bring the minus 4, we're going to get 2k minus 1 is greater than 0. Now this is true as k is greater than equal to 3. Okay, so this is going to be true for p of k plus 1. If p of k is true, hence, by the principle of mathematical induction, p of n is true. Now guys, the key step to realise was that when we multiplied this out, we replaced 2k squared. See the 2k squared? The 2k squared, which is representative of p of k, got replaced with a smaller number. So this number here got replaced with this here, which is actually a smaller number than 2k squared. And when we proved that this smaller number plus the number we had was bigger than this number anyway, therefore the bigger number has to be bigger than it as well. Okay, so it's like an intermediate step. Okay, so part 3, question 3. We're gonna test P of 1. So when you test P of 1, you're going to get A plus B to the power of 1 greater than A1 plus B1. Now, this here should be greater than or equal to. Okay, so just the question has a small mistake there, so it's going to be A1 plus B1. And what we're going to get there is that A plus B is greater than or equal to A plus B. Okay, and this is true for P of 1. Okay, next we're going to assume true for P of K. So step 2, assume true for P of K. Now when we assume true for P of K, what we're going to get is A plus B to the power of K greater than AK plus BK. Now, then part 3 is test P of K plus 1. And P of K plus 1 is going to be A plus B to the power of K plus 1 greater than AK plus 1 plus BK plus 1. Now what we're going to do is we're going to try and make P of K plus 1 very similar to P of K if we can. So we're going to break this up into A plus B by A plus B to the power of K, breaking up my index. Then we're going to have A times A to the K plus B times B to the K. Now, if I replace this number here, I'm going to replace with a smaller than or equal, replace with a less than or equal, so replacing a number with a smaller number. Okay, so I'm replacing it with AK plus BK. So I'm going to replace that with AK plus BK, because we know that this number here is bigger than 2 of this. So what we're going to get then is we're going to get A plus B to the power, and then multiply that by AK plus BK greater than or equal to AK plus B BK. Now multiply by AK and we get AK, then we get plus A BK, then plus B AK, and then plus B BK. And we have to prove that this is greater than or equal to AK plus B BK. Now you can see on both sides that the AK is cancelled, the B BK is cancelled, and I'm going to be left with A multiplied by B to the power K plus B by A to the power K greater than or equal to 0. Now, this is true as A and B are bigger than 0, because we're told they're bigger than 0, and K is bigger than 0. So, hence, true for P of K plus 1 if P of K is true. Hence, by the principle of mathematical induction, P of n is true. Okay, moving on to question 5. Now, in question 5, what we have here is 3 to the power of n is bigger than 2n plus 1 for n greater than 1. n greater than 1 means that P of 2 is our starting point. So we're going to test P of 2. We test P of 2, we're going to get 3 squared greater than 2 multiplied by 2 plus 1. 9 is greater than 5. So this is true for P of 2. Now, after that, we're going to assume true for P of k. Where k is greater than 1. So 3 to the power k is greater than 2k plus 1. Now, part 3, we're going to test P of k plus 1. And we have here is 3 times 3 to k plus 1 greater than 2k plus 1 plus 1. And we're going to get here is 3 times 3 to the k greater than equal to 2k plus 2 plus 1 plus 2 plus 1 obviously gives me a plus 3. Now, we're going to replace this number replace with 2k plus 1, because we know that 2k plus 1 is a smaller number than 3 to the power of k. So 3 to the power of 2k plus 1 is greater than 2k plus 3. Then we're going to have 6k plus 3 is greater than 2k plus 3. Then bring these over to your side, you slash them off, and we get 4k is greater than 0. And this is going to be true for P of k plus 1 if P of k is true. Okay, part 3, and hence by the principle of mathematical induction, it's true for P of n. So 4 to the power of n is greater than 3n squared plus 1. So we're going to test for P of 1. And we test for P of 1, we're going to get 4 to the power of 1 greater than equal to 3 times 1 squared plus 1. 4 greater than equal to 4. True for P of 1. Now, do next is assume true for P of k. And assume true for P of k, you're going to get 4 to the power of k greater than equal to 3k squared plus 1. Part 3, test for P of k. So therefore, we're going to have 4 to the power of k plus 1 is greater than 3 times k plus 1 squared plus 1. We're going to have 4 times 4 to the power of k greater than, and that's going to be k squared plus 2k plus 1. That's 3k squared plus 6k plus 3 plus 1. Then we're going to get 3k squared plus 6k plus 4. Okay. Now what I need to do is I need to replace 4 to the power of k. Again, replace with 3k squared plus 1. Now it's going to be 4 multiplied by 3k squared plus 1 greater than equal to 3k squared plus 6k plus 4. We're going to get 12k squared plus 4 greater than equal to, and we'll move the other numbers all over your side. The 4s will cancel. Then we're going to get minus 3k squared minus 6k greater than 0. And then what we're going to get is 9k squared minus 6k greater than 0. Now this is going to mean this is going to be 3k so this is question 7. So what we got to prove here is that 9k squared is greater than 6k, and as k is greater than or equal to 1. So what we could do here, now you say this is true as k is greater than or equal to 1, because 9k squared greater than 6k. Now what we could also try here is say 9k squared minus 6k is greater than 0, and then what we could also say then is we took out k, 3k, and we're going to get 3k minus 2 is greater than 0. So 3k is greater than 0 as k is greater than or equal to 1, and 3k minus 2 is greater than or equal to 0. Oh, sorry, it's greater than 0 as k is greater than or equal to 1. Okay, so this is true for p of k plus 1 if p of k is true. Hence, by the principle of mathematical deduction, p of n is true. Okay, and finally question 9. Now, what we got to do here, got to prove for p of 1. So, prove p of 1. It's going to be 1 over 1 plus r to the power 1 divided by 1 minus 1 times r. That's going to be 1 over 1 plus r less than or equal to 1 over 1 plus r. Okay, so true for p of 1. Now, moving on, assume true for p of k. Now, in p of k, we're going to have 1 plus r to the power k greater than or equal to 1 plus kr. Now, we're going to start off and then we're going to test p of k plus 1. Now, p of k plus 1 is equal to 1 plus r to the power k plus 1 greater than or equal to 1 plus k plus 1 times r. So it's going to be 1 plus r multiplied by 1 plus r to the k is greater than or equal to 1 plus kr plus r. Now we're going to replace this number here with a smaller number. We're going to replace it with 1 plus kr. And then we're going to get is 1 plus r into 1 plus kr is greater than or equal to 1 plus kr plus r. Multiply this out and you get 1 plus kr plus r plus kr squared. greater than or equal to 1 plus kr plus r. Kr cancels, 1 cancels, and r cancels. Kr squared is greater than or equal to 0.
Good morning. Here are today's announcements. First of all,
so kr squared is greater than 0 as k is greater than 0 and k is element n, excuse me. K is element n and r is greater than 0. So true for p of k plus 1 if p of k is true. Hence, by the principle of mathematical deduction, p of n is true.